So in this lecture, we are going to study about electric potential due to a dipole. Now, as we all know that a dipole has equatorial line, axial line, and there are many other points which lie neither on the axial line nor on the equatorial line. So what we'll do is we'll find the electric potential at a general point, and then we will see the special cases of axial line and equatorial line. So suppose this is a dipole having a charge of plus q and minus q, and the distance, as we all know, what we do is we keep this distance as 2a, so that from the center the distance of each charge becomes a. Now I take a line which makes an angle theta with this dipole. Now there is a point on this line which is at a distance r. So from the center the distance is r. From plus q, the distance is slightly smaller than r, and from minus q, the distance is slightly larger than r. This also I can keep as theta. So now what I will do is I will mark these points. Suppose I write this point as capital Q, this point as capital R, this point as X. Then from this point Q, I drop a perpendicular on PX. This point is Y. So we can, because this QX is A and this RX is also A, so we can write in triangle Q X Y, this is Y, cos theta is equal to XY, this is X. If you are confused, this is X, this is Y. So cos theta is equal to XY upon A. So XY will be equal to A cos theta. Now this PQ is approximately equal to PY, which is equal to PX minus XY. So this PQ will be approximately equal to R minus A cos theta. I put this in rectangular box so that I can remember it. Now what I do is I drop another perpendicular from R to this PX extended, and suppose this point I take as Z. So there will be a triangle RXZ. So in this triangle RXZ, I can write cos theta is equal to Rz upon A. So Rz will again be equal to A cos theta. Now this PR will approximately be equal to PZ, and this PZ is equal to PX plus XZ. So PR will be approximately equal to Px, which is R, plus Xz, which is A cos theta. Now, uh, the potential at the point P will simply be Kq upon PQ plus K minus Q upon PR. So I will slide this up. So Vp will be equal to Kq 1 upon PQ minus 1 upon PR. So this will be Kq, and 1 upon PQ is R minus A cos theta minus 1 upon PR is R plus A cos theta. We have to solve it completely. This will be Kq R square minus A square cos square theta, and then we'll get R plus A cos theta minus R minus A cos theta. Now R and R will cancel, and A cos theta plus A cos theta will give 2A cos theta. So 2KQ A cos theta divide by R square minus A square cos square theta. This will be V. Now 2QA. This 2QA gives us P vector magnitude, which is called dipole moment. So I can write this V as 2, no, not 2, K P cos theta upon R square minus A square cos square theta. Now this is the exact formula, but what we do is normally practically the length of the dipole is very small. So I write here that for a short dipole, this A is very small compared to R. So in comparison between R and A cos theta, I will neglect R. So neglecting A cos theta in comparison to R, the formula will come K P cos theta upon R square. So this is the formula which we have to use, Kp cos theta upon r square. Now there is one more thing, like we can see, suppose this is a dipole, plus q minus q, and this is the dipole moment. So previously I had not made the dipole moment, but now I will make it. And there is a point here, and this is r. So at the point P, there is no direction of potential because potential is a scalar. This is angle theta. So angle between P vector and R, suppose I take it R vector, it is theta. So the formula is Kp cos theta upon R square. What I do is, here I write K P cos theta upon R square, and then I multiply with R and divide by R, because nothing is going to happen if you multiply and divide with the same quantity. So I will get V is equal to K P R cos theta upon R to the power 3. So this P R cos theta gives us K P vector dot R vector upon R to the power 3. This also proves that it is a dot product, so it has to be scalar. So at this P point, the potential will be Kp cos theta upon R square. Now, as we can see, there is an axial line. There is also an equatorial line. So first I write for the equatorial line. Equatorial line. Now in equatorial line, suppose this is plus q, this is minus q, and this line, which we call the equatorial line, this is a point P. The dipole moment is from minus q to plus q, and this point P, we can draw R like this. This is P, and angle between P and R will be 90. So V will be equal to K P cos 90 upon R square, which will give us 0. So at the equatorial line, the electric potential is 0. On the axial line, let us take another case on the axial line. On the axial line, actually what happens, this is the axial line. This is the dipole moment, and this is the axial line. Now axial line has 2 points. Suppose I make one point A here and another point B here. So if we take at A, so from center we draw the position vector. This is R. So you can see that the angle between P and R is 0. So the potential at A will be K P cos 0 upon R square, which means K P upon R square. Potential at the point A. At B, if we draw the position vector from the center to the point B, Again, this distance is r, but you can see that angle between P and R is 180. So at B, the potential will be Kp cos 180 by R square. So Vb will be equal to minus Kp upon R square. So on the same equatorial line, potential can come out to be positive also and negative also. Positive is when it is closer to the positive charge, like at the point A, and negative is closer to the negative charge, like the point B. So this was the complete theory about potential due to a dipole.